There's tension force X and tension force Y. Tension force makes a 27-degree angle. Okay, so I hope that your trig skills are strong enough now that it's clear to you that tension force X, let's see, again, we know that tension force X is going to be in the negative direction. I guess I should have chosen my positive direction. So let's choose up and to the right as our positive directions. Those are the standard positive directions. So then left would be negative. And that would be negative 4,900 times the cosine of 27 degrees. Tension force X here is adjacent to the 27 degrees, so we should use the cosine. So we can look that up in the calculator, and we would get 900 times cosine 27. So we get that tension force X is negative 4366. I'm just going to round that off to 4366. And you might have noticed that in the tutoring session we were not worried about significant figures at all. So I'm going to continue not to worry about significant figures and just round things off to what feels natural. So I'm going to round this off to 4366. Okay, and by the same token we can find tension force Y. Now the overall tension force was pointing up and to the left. So the components were pointing up and to the left. So tension force Y is pointing up in the positive direction. The hypotenuse is 4,900. Tension force Y is opposite to the 27 degrees, so we use the sine. And we get that tension force Y is positive 2225 newtons approximately. 2225 newtons approximately. All right, so that gives us tension force X and tension force Y. And now we can plug in. Again, we don't know the hinge force, but now we know that tension force X is 4366. Negative because it's moving to the left. How about the right-hand side here? Well, we do know what the mass is. We do know what the mass is. The mass is just the mass of the boom plus the mass of the signs. The mass would just be 50 kilograms plus 200 kilograms or 250 kilograms. But I'm not even going to bother plugging that in. I'm not even going to bother plugging in for the mass. Why not? Because I know that acceleration x is 0, right? We already discussed this. This is a statics problem. The whole apparatus is supposed to be held motionless over a period of time. Well, if you're motionless over a period of time, your velocity is constant at 0, and when your velocity is constant, your acceleration is 0. And then again, we don't even need to bother worrying about the mass, even though we could figure it out, because when we multiply the mass by 0, it's just going to end up being 0. So there is a mass, but we don't care what it is because that mass is going to get multiplied by 0 and leave the right-hand side as 0. Now let me stop and remind you again why it was important to do the torque equation before the force equation. Remember, what would have happened if we had started with this force equation before we had done the net torque equation? Well, then there would have been two unknowns, because then we would have been in this situation where we didn't know the hinge force or the tension force. Remember that when the problem started, we don't know the hinge or the tension force. So if we had started at the beginning of the problem with the net force equation, this would not be very useful because there would be two unknowns, both the hinge force and the tension force. It's only after we used the net torque equation that we were able to figure out what the overall tension was. And only once we knew the overall tension was it easy to figure out the x and y components of the tension and plug in. So it really was to our advantage that we used the net torque equation first. All right, and then with just a little algebra, we would get that the hinge force here in magnitude is 4366 newtons. Notice that mathematically, the hinge force here came out, mathematically, the variable here came out to be positive, and that really has to be the case because remember that we're just using this to stand for a magnitude, and magnitudes have to be positive. All right, so we got that hinge force X is 4366 newtons. Let's go ahead and do the same thing for hinge force Y. Maybe I'm going to do that on a separate page. Okay, so we've got net force Y equals MAY. And let's see, we've got hinge force Y. Now, we guessed that hinge force Y was pointing up. Since we guessed that hinge force Y is pointing up, I'll put a plus sign in front of it. And now that I put that sign in, I'm going to put a dot in to show that the variable here just stands for the magnitude. I like to use a dot when I'm using a variable just to stand for a magnitude. That's just a symbol I made up. We guessed that hinge force Y was pointing up, so I've already put in that positive sign. Then we have the weight of the beam going down, and the weight of the sign going down, and we've got tension force Y going up. Again, we've seen that tension force Y is pointing up because the overall vector was pointing up and left. Hinge force Y, we don't know. The weight of the beam we calculated was, whoops. What was the weight of the beam? That was 490 newtons. Weight of the beam is 490 newtons. Down. The weight of the sign is 1960 newtons. Down. Tension force Y. Tension force Y, we calculated was positive 2225 newtons. We calculated tension force Y here, so that's plus 2225 newtons. Okay, so we've plugged in now for each of our forces. And remember again, you can see the advantage to having used the net torque equation first. Until we used the net torque equation, we would not have known what tension force was, and so we would not have been able to plug in for the Y component of the tension. So it's good that we used the net torque equation first and only later use the net force equations. Okay, and again, we can simplify this right-hand side. Again, because this is a statics problem, the acceleration is 0, so the whole right-hand side becomes 0. We don't even have to bother plugging in for the mass.